You never see it, never hear it, but it holds you to Earth, binds the moon above, and sculpts the motion of galaxies. Gravity, the weakest of all forces, and yet the most cosmic. But how does it actually work? Right now, as you sit or stand, you're experiencing one of the universe's greatest mysteries. Every atom in your body is being pulled toward the center of our planet by an invisible force that we still don't fully understand. This same force keeps our atmosphere from drifting into space, creates the tides that wash our shores, and holds together the vast cosmic web of galaxies that stretches across billions of light years. Gravity is everywhere, yet it remains the most enigmatic of nature's fundamental forces. We can measure it precisely, predict its effects with stunning accuracy, and even detect its ripples traveling through space-time itself. But ask a physicist to explain exactly how gravity works at its deepest level, and you'll discover we're still searching for answers. What makes gravity so mysterious? Unlike the other forces of nature, gravity doesn't seem to fit the rules. It's incredibly weak compared to electromagnetism or the nuclear forces, yet it dominates the large-scale structure of the universe. It appears to act instantly across vast distances, yet we know nothing can travel faster than light. It feels like a pulling force, yet Einstein showed us it might not be a force at all. This is the story of humanity's quest to understand the invisible architect of the cosmos. From Newton's falling apple to Einstein's curved space-time, from the discovery of gravitational waves to the search for quantum gravity, we'll explore how our understanding of this fundamental phenomenon has evolved and where the deepest mysteries still lie. We'll journey from the familiar sensation of weight to the mind-bending physics of black holes, from the laboratory experiments that test Einstein's predictions to the theoretical frontiers where space and time themselves might emerge from something even more fundamental. Along the way, we'll discover that gravity isn't just another force, it's the very fabric of reality itself, woven into the structure of space and time. To understand gravity, we have to begin, not with space, but with weight. Step outside and jump. For a brief moment, you're weightless, floating free from the Earth's grip. But then something pulls you back down. Your feet hit the ground with a satisfying thud, and you feel the familiar sensation of your own weight pressing through your legs. This everyday experience seems so simple, so obvious. Of course you fall down instead of up. Of course you have weight. But what you're actually experiencing is far stranger than it appears. That sensation you call weight, that feeling of being pulled toward the earth, isn't actually gravity pulling you down. It's the ground pushing back up against you. Right now, as you read this, you're not sitting still. You're accelerating. Not through space, but through something far more fundamental. You're accelerating through the very fabric of space-time itself. Think about it this way. Imagine you're in an elevator and someone cuts the cables. As you and the elevator plummet toward the ground, you would float weightlessly inside the falling elevator. You wouldn't feel gravity at all. In that moment of free fall, you would be following your natural path through space-time, unimpeded by any forces. It's only when the elevator hits the ground, when something stops your natural motion, that you feel weight again. This reveals something profound about the nature of gravity. What we experience as the force of gravity isn't actually gravity itself. It's our resistance to gravity. It's the electromagnetic forces in the atoms of the ground pushing back against our attempt to follow our natural path through curved space-time. The earth beneath your feet is constantly accelerating you upward, away from the geodesic, the natural path that you would follow if left to move freely through space-time. When an apple falls from a tree, it's not being pulled down by some mysterious force reaching out from the Earth's center. Instead, it's following the straightest possible path through space-time that has been curved by the Earth's presence. It's moving in a straight line through curved space, just as a marble rolling across a curved surface follows what seems like a curved path, but is actually the straightest possible route across that curved surface. This same principle governs everything from the smallest pebble to the largest celestial body. When you throw a ball, its parabolic arc through the air isn't the result of two forces competing, one pushing it forward and gravity pulling it down. It's a single unified motion along a geodesic through curved space-time. The ball is simply following the geometry of space itself. Look up at the moon on a clear night. That pale sphere hanging in the sky isn't being held there by invisible strings or mystical forces. It's following its natural path through the curved space-time around Earth. The moon is actually falling toward Earth constantly, but the curvature of space-time is such that as it falls, it also moves sideways, creating the orbital motion we observe. The moon is in perpetual free fall, following a geodesic that curves around our planet. This same principle explains the majestic dance of the planets around the Sun. Mercury, Venus, Earth, Mars, and all the others aren't being grabbed and pulled by solar gravity. They're simply following the natural contours of space-time that have been curved by the Sun's immense mass. Each planet traces out its elliptical orbit by following the straightest possible path through this curved cosmic landscape. The effects of this space-time curvature extend far beyond simple orbital mechanics. Consider the tides that rise and fall along our coastlines twice each day. These aren't caused by the moon pulling on our oceans. Instead, they result from the fact that space-time curvature varies slightly from one location to another. The side of Earth closest to the moon experiences slightly stronger curvature than the side farthest away. This differential curvature stretches our planet slightly, creating the tidal bulges that we experience as high and low tides. Even our atmosphere owes its existence to this curved space-time. The air molecules that surround us, from the oxygen we breathe to the nitrogen that makes up most of our atmosphere, are all following geodesics through the curved space-time around Earth. Without this curvature, these molecules would simply drift away into space, following straight-line paths into the cosmic void. The fact that we can breathe, that we have weather patterns and atmospheric pressure, all depends on the way Earth's mass curves the space-time around it. This curvature affects everything with mass or energy. Light itself, though it has no mass, still follows the curved paths through space-time. When light from distant stars passes close to the sun, it bends slightly, following the curvature that the sun creates in space-time. This effect, called gravitational lensing, allows astronomers to see galaxies that would otherwise be hidden behind closer objects, as the gravity of intervening matter acts like a cosmic magnifying glass. But here's where things get truly mind-bending. Time itself is affected by this curvature. Clocks run slightly slower in stronger gravitational fields. A clock on the ground floor of a tall building runs slightly slower than an identical clock on the top floor. The difference is tiny, measured in billionths of a second, but it's real and measurable. The global positioning system satellites that help navigate our modern world must account for this time dilation, or their location calculations would be off by miles. This means that your head is literally aging faster than your feet. The difference is unimaginably small, but it's there. Every moment of your life, time is passing slightly faster for the atoms in your brain than for the atoms in your toes. Gravity doesn't just curve space, it curves time as well, creating a four-dimensional space-time that shapes the very flow of temporal experience. All of these phenomena, from the falling apple to the orbital ballet of planets, from ocean tides to the aging of your atoms, stem from a single elegant principle. Mass and energy tell space-time how to curve, and curved space-time tells matter how to move. What we experience as gravity is simply the result of moving through this curved cosmic landscape. The profound implications of this curved space-time extend into every corner of our existence. Consider the simple act of walking. Each step you take is actually a complex interaction with curved space-time. As you lift your foot and move it forward, you're temporarily entering a slightly different region of space-time curvature. The sensation of your foot hitting the ground isn't just contact between solid objects. It's the moment when the electromagnetic forces in the pavement push back against your attempt to follow your natural geodesic path through curved space-time. When you feel heavy after a long day, you're not just experiencing fatigue. You're feeling the constant work that your body must do to resist following its natural path through space-time. Every muscle fiber, every bone, every cell in your body is being continuously accelerated upward by the electromagnetic forces that keep you from sinking into the earth. Standing upright isn't a passive state, it's an active resistance to the curvature of space-time itself. Even the way objects break and shatter reveals the nature of space-time curvature. When you drop a glass and it hits the floor, the shattering isn't caused by the impact alone. It's the result of different parts of the glass trying to follow slightly different geodesic paths through curved space-time. The bottom of the glass hits the floor first and is forced to stop its natural motion, while the top continues to follow its geodesic path downward. This differential creates stress that exceeds the molecular bonds holding the glass together, causing it to fracture. The blood flowing through your veins and arteries is also affected by this curvature. Your heart must work slightly harder to pump blood to your brain because it's moving that blood to a region of slightly different space-time curvature. The difference is minute, but it's measurable. Medical researchers studying the effects of long-term space travel have found that the absence of significant space-time curvature affects everything from bone density to cardiovascular function. Plants and trees provide another fascinating example of life adapting to curved space-time. The way a tree grows, reaching its branches toward the sky, isn't just a response to sunlight. It's also a response to the gradient of space-time curvature around Earth. Roots grow down not because they're pulled by gravity, but because they're following the natural geodesic paths through increasingly curved space-time as they approach Earth's center. The entire architecture of life on Earth has evolved in response to the geometry of curved space-time. Weather patterns, too, are manifestations of this curvature. When warm air rises and cool air sinks, these aren't just temperature-driven processes. They're the result of air masses with different densities following different geodesic paths through curved space-time. Hurricanes and tornadoes are massive spiraling structures that emerge from the complex interaction between atmospheric dynamics and the underlying geometry of space-time itself. Even sound waves are affected by space-time curvature. The reason your voice sounds different at the top of a mountain compared to sea level isn't just due to air density changes. Sound waves, being patterns of molecular motion, follow paths that are influenced by the local curvature of space-time. The speed of sound varies slightly with altitude, not just because of temperature and pressure changes, but because time itself flows at a slightly different rate. The water in your coffee cup right now is sitting at an equilibrium that represents a balance between molecular motion and space-time curvature. The surface of the liquid is perpendicular to the local geodesic paths through curved space-time. If you could somehow turn off gravity, that water wouldn't just float away. It would follow straight line paths through uncurved space-time, expanding into a sphere as the molecular motion overcame the electromagnetic forces holding the liquid together. Buildings and structures around you are all designed to work with and against space-time curvature. The foundations of skyscrapers must bear enormous loads, not just because of the weight of the materials above, but because those materials are all being constantly accelerated upward by the electromagnetic forces in the foundation, resisting their natural tendency to follow geodesic paths through curved space-time. Every bridge, every tunnel, Every architectural marvel represents humanity's engineering response to the geometry of curved space-time. The technology that surrounds us daily also depends on understanding these effects. The precise timing required for cellular phone networks relies on accounting for the slight differences in how time flows at different altitudes. The GPS satellites orbiting overhead must continuously correct for the fact that time moves slightly faster in their weaker gravitational field. Without these corrections, your navigation system would accumulate errors of several miles per day. Even the light by which you're reading these words has been affected by its journey through curved space-time. If this light came from the sun, it has traveled through the curved space-time around our star, across the curved space-time of the solar system, and through the curved space-time around Earth. Each photon has followed a geodesic path, the straightest possible route through this curved cosmic landscape. But for centuries, we didn't understand any of this. We knew that things fell down, that planets orbited the sun, that tides rose and fell, but we had no idea why. We experienced all these phenomena daily, built our lives around them, but the underlying mechanism remained hidden. The breakthrough came from a man sitting under a tree, watching fruit fall from its branches, and wondering if the same force that pulled the apple down might also keep the moon in its orbit around Earth. Isaac Newton never actually sat under an apple tree and watched fruit fall on his head. That story, charming as it is, was probably invented years later. But Newton did have a revolutionary insight that changed our understanding of the cosmos forever. He realized that the force pulling an apple toward Earth might be the very same force keeping the moon in orbit around our planet. This simple idea unified terrestrial and celestial mechanics for the first time in human history. Before Newton, the heavens and Earth seemed to operate by completely different rules. Aristotle had taught that earthly objects naturally fell toward the center of the world because that was their proper place, while celestial bodies moved in perfect circles because that was their divine nature. The idea that a falling rock and an orbiting planet might be governed by the same physical law was revolutionary, almost heretical. Newton's breakthrough came from his ability to see patterns where others saw separate phenomena. He imagined a cannonball fired from a mountaintop with increasing velocity. Fire it slowly, and it falls to Earth nearby. Fire it faster, and it travels farther before hitting the ground. But fire it fast enough, Newton reasoned, and the curvature of the Earth itself would come into play. The cannonball would fall toward Earth, but Earth's surface would curve away beneath it at the same rate. The cannonball would orbit the planet, falling continuously, but never hitting the ground. This thought experiment led Newton to his law of universal gravitation, one of the most elegant and powerful equations in all of physics. The gravitational force between any two objects, he proposed, equals the gravitational constant times the product of their masses, divided by the square of the distance between them. In mathematical terms, F equals g times m sub 1 times m sub 2 divided by r squared. This deceptively simple equation revealed profound truths about the universe. Every object with mass attracts every other object with mass. The force is always attractive, never repulsive. It acts along the line connecting the centers of the two objects. And most remarkably, it follows an inverse square law, meaning that doubling the distance between objects reduces the gravitational force by a factor of 4. The inverse square relationship turned out to be crucial for the stability of planetary orbits. If gravity followed an inverse cube law, planets would either spiral into the sun or fly off into space. If it followed an inverse first power law, orbits would be unstable in different ways. Only the inverse square relationship allows for the stable, elliptical orbits we observe throughout the solar system. Newton's law explained why Kepler's earlier observations of planetary motion worked so well. Johannes Kepler had discovered that planets sweep out equal areas in equal times as they orbit the Sun, and that the square of a planet's orbital period is proportional to the cube of its average distance from the Sun. These seemed like mysterious mathematical relationships until Newton showed they were natural consequences of an inverse square gravitational force. The universality of Newton's law was breathtaking. The same equation that described an apple falling from a tree also explained the orbit of the Moon around Earth, the motion of the planets around the Sun, and even the behavior of double star systems in distant parts of the galaxy. For the first time, humans had a single mathematical description that applied to gravitational phenomena everywhere in the universe. Newton's law also explained the tides with unprecedented precision. The Moon's gravitational pull on Earth's oceans creates two bulges, one on the side facing the Moon and another on the opposite side. As Earth rotates beneath these bulges, any given location experiences two high tides and two low tides each day. The Sun also contributes to tidal forces, creating the especially high spring tides when Sun and Moon align, and the more modest neaptides when they're at right angles. The law even predicted phenomena that hadn't been observed yet. Edmund Halley used Newton's equations to calculate the orbit of the comet that now bears his name, predicting its return in 1758, 16 years after his own death. When the comet appeared exactly as predicted, it provided dramatic confirmation of Newton's gravitational theory. Perhaps most remarkably, Newton's law revealed that gravity has infinite range. Unlike other forces that seem to require direct contact, gravitational attraction operates across any distance, no matter how vast. The Sun influences the motion of planets billions of miles away. The gravity of distant stars affects the orbits of comets at the very edge of our solar system. Every galaxy in the universe exerts some gravitational influence on every other galaxy, no matter how far apart they are. This infinite range created a puzzle that troubled Newton himself. How could the Sun instantly know about the presence of Earth, 93 million miles away, and adjust its gravitational pull accordingly? Newton's equations described what gravity did with extraordinary accuracy, but they said nothing about how gravity worked. Newton famously wrote, "I frame no hypotheses about the mechanism behind gravitational attraction." The instantaneous action at a distance implied by Newton's law seemed almost magical. If the Sun suddenly vanished, Newton's equations suggested that Earth would immediately fly off in a straight line, even though light from the Sun would take 8 minutes to reach us with news of the Sun's disappearance. This implied that gravitational influence could travel faster than light, potentially faster than anything in the universe. Despite this conceptual difficulty, Newton's law proved extraordinarily successful for practical calculations. Engineers used it to design bridges and buildings, taking into account the gravitational loads on structures. Astronomers used it to predict eclipses, map the orbits of asteroids, and search for new planets. When irregularities in Uranus's orbit suggested the presence of an unknown planet, astronomers used Newton's law to calculate where this planet should be, leading to the discovery of Neptune in 1846. The law also revealed subtle effects that had never been noticed before. Newton showed that Earth isn't perfectly spherical, but is slightly flattened at the poles due to its rotation. The gravitational field of this oblate Earth causes the orbits of satellites to slowly precess or shift their orientation over time. These tiny effects could be calculated precisely using Newton's equations. Newton's gravitational theory even explained why we have seasons. Earth's tilted axis means that different hemispheres receive varying amounts of solar energy throughout the year, but gravity keeps our planet in a stable orbit at just the right distance from the Sun to maintain liquid water and support life. The success of Newton's law was so complete that it seemed to explain everything about gravity. For more than 2 centuries, scientists found no phenomena that couldn't be accounted for by Newton's inverse square law. The theory passed every test, explained every observation, and made countless successful predictions. But there were hints that something deeper was going on. The most precise observations of Mercury's orbit showed tiny discrepancies that Newton's law couldn't explain. The planet's elliptical orbit slowly rotated, or precessed, slightly faster than Newton's theory predicted. The difference was minuscule, only 43 arcseconds per century, but it was real and measurable. Most scientists assumed this small discrepancy would eventually be explained by some previously unknown factor, perhaps another planet orbiting closer to the Sun, or a slight deviation in the Sun's shape from perfect sphericity. Few suspected that the problem lay with Newton's law itself. There was also the nagging philosophical problem of action at a distance. How could objects influence each other across empty space without any intervening medium? Some scientists proposed that space was filled with an invisible ether that somehow transmitted gravitational forces, but no one could detect this hypothetical substance or explain how it worked. Newton had given humanity its first truly universal physical law, a mathematical description of gravity that worked everywhere, from falling apples to orbiting galaxies. His theory revealed the fundamental unity underlying all gravitational phenomena and provided the foundation for centuries of scientific and technological progress. But Newton himself recognized that his law was incomplete. It described what gravity did with incredible precision, but it left the deeper question unanswered. How does gravity actually work? The answer would come from a young patent clerk in Switzerland, who would show that gravity wasn't a force at all. Albert Einstein was 26 years old when he had what he later called the happiest thought of his life. It came to him in 1907 while he was working at the Swiss Patent Office in Bern. He imagined a person falling freely from the roof of a house. During the fall, Einstein realized the person would not feel their own weight. They would experience weightlessness, just like an astronaut in orbit around Earth. This simple insight would revolutionize our understanding of gravity and reshape our conception of space and time itself. Einstein's revelation was that there's no way to distinguish between being in free fall and being in a region of space completely free from gravitational fields. A person falling in an elevator with no windows couldn't tell whether they were plummeting toward Earth or floating in deep space far from any massive objects. This became known as the equivalence principle, and it suggested something profound about the nature of gravity. If you can't tell the difference between free fall and floating in empty space, Einstein reasoned, then maybe they're actually the same thing. Maybe what we call gravity isn't a force at all, but rather the natural state of motion through curved space-time. When you're standing on Earth's surface, you're not at rest. You're being constantly accelerated upward by the electromagnetic forces in the ground beneath your feet, preventing you from following your natural path through curved space-time. This was a complete reversal of our intuitive understanding. In Newton's picture, gravity was a force that pulled objects toward each other across empty space. In Einstein's new vision, there was no gravitational force at all. Instead, massive objects curved the fabric of space-time itself, and other objects simply followed the straightest possible paths through that curved geometry. To understand this revolutionary idea, imagine a bowling ball placed on a stretched rubber sheet. The ball creates a depression in the sheet, curving its surface. Now roll a marble across the sheet. Instead of traveling in a straight line, the marble will curve around the depression created by the bowling ball. The marble isn't being pulled by any force emanating from the bowling ball. It's simply following the straightest possible path across the curved surface of the sheet. Einstein proposed that massive objects do something similar to the fabric of space-time. The Sun creates a large depression in space-time, and Earth follows a curved path around this depression. From Earth's perspective, it feels like we're being pulled by the Sun's gravity. But in Einstein's picture, Earth is actually following a geodesic, the straightest possible path through the curved spacetime around the Sun. This geometric view of gravity explained many puzzles that had troubled Newton's theory. The problem of action at a distance disappeared. Objects don't need to reach across empty space to influence each other. Instead, they curve the spacetime around them, and this curvature affects the motion of nearby objects. The influence propagates through spacetime at the speed of light, not instantaneously as Newton's theory suggested. Einstein's theory also made a startling prediction about time itself. In regions of stronger gravitational fields, where spacetime is more severely curved, time should run slower. This phenomenon, called gravitational time dilation, means that a clock near a massive object will tick more slowly than an identical clock farther away from the massive object. This isn't just a theoretical curiosity. The effect is real and measurable. A clock on the ground floor of a tall building runs slightly slower than a clock on the top floor. The difference is tiny for everyday situations, only about 90 nanoseconds per day for a 300-meter height difference, but it's been confirmed by incredibly precise atomic clocks. The Global Positioning System provides a practical demonstration of gravitational time dilation every day. The satellites orbiting Earth experience weaker gravity than we do on the surface, so their onboard clocks run about 38 microseconds per day, faster than identical clocks on Earth. If this effect weren't corrected, GPS calculations would accumulate errors of about 6 miles per day, making the system useless for navigation. Einstein's geometric theory of gravity made other testable predictions that distinguished it from Newton's force-based model. Light, even though it has no mass, should follow curved paths through curved space-time. This meant that light from distant stars should bend when passing close to the Sun. Newton's theory also predicted some bending of light, but Einstein's theory predicted exactly twice as much. The opportunity to test this prediction came during a total solar eclipse on May 29, 1919. Arthur Eddington led expeditions to observe the eclipse from the island of Principe off the coast of West Africa and from Sobral in Brazil. By photographing stars visible near the Sun during the eclipse and comparing their apparent positions to their known positions when the Sun was elsewhere in the sky, Eddington could measure how much the Sun's gravity bent starlight. The results confirmed Einstein's prediction and made him instantly famous around the world. Newspaper headlines proclaimed that Newton had been overthrown and that space was curved. The measured deflection of starlight matched Einstein's theoretical calculation within the experimental uncertainty, providing dramatic confirmation that gravity really was the curvature of space-time. Einstein's theory also explained the mystery of Mercury's orbital precession that had puzzled astronomers for decades. In Newton's theory, planets should follow perfect elliptical orbits that maintain the same orientation in space. But Mercury's orbit was observed to slowly rotate, with the point of closest approach to the Sun advancing by 43 arc-seconds per century, more than Newton's theory predicted. Einstein's field equations, which describe how mass and energy curve spacetime, predicted exactly this additional precession. The calculation was fiendishly difficult, involving solving Einstein's highly non-linear differential equations for the curved spacetime around the Sun. But when Einstein finally worked through the mathematics, the result matched the observed precession of Mercury's orbit precisely. This success was particularly satisfying because it explained an existing anomaly rather than predicting a new effect. Einstein hadn't adjusted his theory to fit the Mercury observations. Instead, the correct explanation emerged naturally from his geometric understanding of gravity. As Einstein later wrote, the calculation gave him palpitations, and he was beside himself with joy for days. The geometric nature of Einstein's theory also revealed why the equivalence principle works so perfectly. All objects, regardless of their mass or composition, fall at the same rate in a gravitational field, because they're all following the same geodesics through curved space-time. A feather and a hammer dropped on the moonfall at exactly the same rate, because the curvature of space-time doesn't depend on the properties of the objects moving through it. This universality of free fall had been observed since Galileo's time, but Newton's theory required a mysterious coincidence to explain it. Newton had to assume that gravitational mass, which determines how strongly an object responds to gravity, always equals inertial mass, which determines how much an object resists acceleration. Einstein's theory showed that this wasn't a coincidence at all. It was a natural consequence of gravity being geometry rather than force. Einstein's field equations revealed that space-time curvature depends not just on mass, but on all forms of energy and momentum. Pressure, stress, energy flow, and even the energy density of electromagnetic fields all contribute to space-time curvature. This meant that light itself, being a form of energy, should create tiny gravitational effects. Even the energy binding protons and neutrons together in atomic nuclei contributes to an object's gravitational influence. The theory also predicted that accelerating masses should create ripples in space-time itself, disturbances that propagate outward at the speed of light. These gravitational waves carry energy away from their sources, causing orbiting objects to gradually spiral inward. The effect is incredibly small for most systems, but it should be measurable for extremely dense objects like neutron stars, orbiting each other at close range. Einstein's geometric theory of gravity represented a complete conceptual revolution. Space and time, which had seemed like the fixed stage on which physical events played out, became dynamic participants in the cosmic drama. Mass and energy told space-time how to curve, and curved space-time told matter how to move. Gravity wasn't a force reaching across empty space, but the very shape of space and time itself. Yet for all its elegance and explanatory power, Einstein's theory raised as many questions as it answered. If space-time could be curved, what exactly was being curved? What was the nature of this four-dimensional fabric that could bend and flex like a rubber sheet? And if massive objects created depressions in space-time, what lay beneath to support the fabric itself? The mathematical framework that Einstein developed to describe curved space-time was unlike anything that had come before in physics. He needed to abandon the familiar, three-dimensional geometry that Euclid had described over 2,000 years earlier and embrace a four-dimensional geometry where space and time were unified into a single mathematical structure called space-time. In this four-dimensional space-time, what we experience as the flow of time is actually motion through the fourth dimension. Every object, even one sitting perfectly still, is moving through space-time at the speed of light. When you're at rest in space, all of your motion is through the time dimension. When you move through space, some of your motion through time gets converted into motion through the spatial dimensions. This is why time slows down for objects moving at high speeds, an effect known as time dilation. The curvature of space-time affects both space and time simultaneously. Near a massive object like Earth, not only do spatial paths curve, but time itself flows more slowly. This means that the geometry of space-time near Earth is fundamentally different from the flat space-time of empty regions far from any massive objects. Clocks, rulers, and even the laws of physics as we experience them are all affected by this curvature. Einstein's field equations describe precisely how matter and energy determine space-time curvature. These equations are deceptively simple in their most compact form, but they represent 10 coupled, nonlinear partial differential equations that are among the most difficult mathematical expressions ever encountered in physics. Solving them exactly as possible only for highly symmetric situations, like the space-time around a perfectly spherical, non-rotating massive object. The solutions to Einstein's equations revealed bizarre and unexpected possibilities. Karl Schwarzschild found the first exact solution just months after Einstein published his theory, describing the curved spacetime around a spherically symmetric mass. This solution predicted that if enough matter were compressed into a small enough region, the curvature of spacetime would become so extreme that nothing, not even light, could escape. These objects, later named black holes, were so strange that even Einstein initially doubted they could exist in nature. Another solution, discovered by Willem de Sitter, described a universe that was expanding exponentially. This seemed so contrary to the assumed static nature of the cosmos that Einstein introduced an artificial term into his equations, the cosmological constant, to prevent this expansion. He later called this the greatest mistake of his career when observations revealed that the universe really is expanding. The geometric nature of Einstein's theory also revealed deep connections between gravity and other areas of physics. The principle of general covariance, which states that the laws of physics must be the same for all observers, regardless of their motion, became a guiding principle for understanding other fundamental forces. The idea that physics should be independent of the coordinate system used to describe it led to profound insights about the nature of physical law itself. Einstein's theory also predicted that rotating massive objects should drag space-time around with them, an effect called frame dragging or the Lense-Thirring effect. Near a spinning black hole, space-time itself is twisted into a spiral pattern, making it impossible for any object to remain stationary relative to distant stars. Everything near the black hole is forced to rotate in the same direction as the black hole's spin. The energy density required to significantly curve space-time is enormous by everyday standards. Earth's gravity, which seems so dominant in our daily experience, actually creates only the tiniest perturbation in space-time geometry. The ratio of Earth's gravitational potential energy to its rest mass energy is only about 1 part in a billion. This is why Newton's theory worked so well for centuries. It's an excellent approximation when space-time curvature is weak. But in extreme environments, where gravitational fields are much stronger, Einstein's corrections to Newton's theory become dramatic. Near the surface of a neutron star, where gravity is hundreds of billions of times stronger than on Earth, space-time curvature becomes so severe that the very concepts of space and time begin to break down in ways that Newton never imagined. The theory even predicted its own limitations. At the centers of black holes and at the moment of the Big Bang, Einstein's equations predict that space-time curvature becomes infinite, creating what physicists call singularities. At these points, the theory itself breaks down, suggesting that some new physics, perhaps involving quantum mechanics, is needed to understand what really happens in these extreme conditions. Einstein's geometric understanding of gravity also revealed why the universe has the large-scale structure we observe. In a perfectly uniform universe with no gravitational attraction, matter would remain spread out evenly forever. But in Einstein's curved space-time, even tiny fluctuations in density can grow over time as matter flows along geodesics toward regions of higher density, eventually forming the galaxies, stars, and planets we see today. The theory made testable predictions about the behavior of light in strong gravitational fields. Photons climbing out of a gravitational well should lose energy and become redshifted, while photons falling into a gravitational well should gain energy and become blue-shifted. This gravitational redshift was first measured in light from the dense white dwarf companion star to Sirius, confirming another prediction of Einstein's theory. Perhaps most remarkably, Einstein's geometric theory of gravity suggested that the universe itself might have a shape and evolution that could be studied scientifically. The same equations that described how planets orbit stars also governed the expansion or contraction of the entire cosmos. This realization would eventually lead to our modern understanding of cosmology and the discovery that we live in an expanding universe that began with the Big Bang. These philosophical puzzles aside, Einstein's theory made concrete testable predictions about the shape of space-time and how this curvature could be measured and mapped. To understand the shape of space-time, we must first abandon our everyday intuitions about geometry. The geometry we learned in school, where parallel lines never meet and the angles of a triangle always add up to 180 degrees, works perfectly for flat surfaces. But space-time isn't flat, it's curved by the presence of mass and energy, creating a four-dimensional landscape of hills, valleys, and warped regions that defies our three-dimensional imagination. Einstein's field equations provide the mathematical recipe for calculating exactly how mass and energy curve space-time. These equations relate the Einstein tensor, which describes the curvature of space-time, to the stress-energy-momentum tensor, which describes the distribution of matter and energy. In the physicists' shorthand, the equations say that geometry on the left equals matter on the right, with Einstein's gravitational constant providing the conversion factor between the two. The mathematics involved is formidable. The Einstein tensor contains terms involving the Riemann curvature tensor, which has 20 independent components in four-dimensional spacetime. Each component is itself constructed from the metric tensor and its first and second derivatives, creating a web of interconnected mathematical relationships that describe how each point in spacetime curves in response to nearby matter and energy. The metric tensor is the fundamental mathematical object that encodes the geometry of spacetime. It tells you how to measure distances and angles in curved spacetime, just as a map projection tells you how to measure distances on the curved surface of Earth using a flat piece of paper. But unlike a simple map, the spacetime metric changes from point to point, creating a dynamic, flowing geometry that responds to the motion and distribution of matter and energy. In regions far from any massive objects, spacetime is nearly flat, and the metric approaches the simple form described by special relativity. Here, the geometry is the four-dimensional analog of a flat tabletop, where geodesics are straight lines and parallel lines remain parallel forever. This is the baseline geometry of empty space, the canvas upon which matter and energy paint their gravitational effects. But near massive objects, the metric becomes dramatically more complex. The presence of mass creates what mathematicians call intrinsic curvature, meaning that the geometry cannot be flattened out without distortion, no matter how clever you are with coordinate transformations. This is fundamentally different from the apparent curvature of, say, a cylinder, which can be unrolled into a flat sheet without changing any distances or angles. The Schwarzschild metric, discovered by Karl Schwarzschild in 1916, describes the curved spacetime around a spherically symmetric, non-rotating massive object like a star or planet. In this geometry, radial distances become stretched and time becomes dilated in a specific mathematical relationship that depends on how close you are to the central mass. The closer you get, the more severe the curvature becomes. This curvature manifests in observable ways. Light traveling radially outward from a massive object must climb against the space-time curvature, losing energy and becoming redshifted in the process. Light traveling tangentially around the object follows curved paths, bending toward the mass. These effects can be calculated precisely using the Schwarzschild metric, allowing astronomers to predict exactly how much starlight will bend when passing near the Sun. The curvature also affects the flow of time itself. In the Schwarzschild geometry, time runs slower closer to the massive object. This isn't just a coordinate effect or an illusion, it's a fundamental property of curved spacetime. A clock dropped toward a black hole would be observed by distant observers to tick more and more slowly as it approaches the event horizon, eventually appearing to freeze at the moment it crosses the point of no return. For rotating massive objects, the geometry becomes even more complex. The Kerr metric, discovered by Roy Kerr in 1963, describes the curved spacetime around a spinning mass. In this geometry, space-time itself is dragged around by the rotation, creating a swirling pattern that forces everything near the rotating object to participate in its spin. Near a rotating black hole, it becomes impossible to remain stationary relative to distant stars, no matter how powerful your rockets. The mathematical description of these curved geometries involves concepts that stretch the limits of human intuition. Geodesics, the straightest possible paths through curved spacetime, can spiral around massive objects, creating the orbital motion we observe for planets and stars. What appears to us as the curved path of a planet around the Sun is actually the straightest possible line through the curved spacetime created by the Sun's mass. Tidal effects arise naturally from the mathematical structure of curved spacetime. The Riemann curvature tensor, which measures how geodesics converge or diverge from each other, directly determines the tidal forces that stretch and squeeze objects moving through curved spacetime. Near a black hole, these tidal forces become so strong they would stretch any falling object into a long, thin shape, an effect colorfully known as spaghettification. The curvature of space-time also determines how gravitational fields interact and combine. Unlike the simple vector addition that works for electromagnetic fields, gravitational effects involve the complex non-linear mathematics of curved geometry. When two massive objects approach each other, their individual space-time curvatures don't simply add together. Instead, they create a new, dynamically evolving geometry that can only be calculated using the full power of Einstein's field equations. This non-linear nature of space-time curvature leads to phenomena that have no analog in Newtonian gravity. Gravitational fields can interact with themselves, creating complex patterns of space-time distortion. Rapidly moving masses can generate gravitational radiation, ripples in space-time itself that carry energy away from their sources. These gravitational waves propagate through space-time at exactly the speed of light, stretching and compressing the very fabric of space as they pass. The geometry of space-time near extremely dense objects reveals effects that seem to violate our everyday understanding of cause and effect. Inside the event horizon of a black hole, the roles of space and time become reversed in a sense. What we normally think of as the spatial direction toward the center of the black hole becomes time-like, meaning that falling toward the singularity becomes as inevitable as moving forward in time. No amount of acceleration can prevent the journey to the center, because it would be like trying to travel backward in time. Even more bizarre geometries are possible in Einstein's theory. Wormholes, hypothetical tunnels through space-time that connect distant regions of the universe, emerge as solutions to the field equations under certain conditions. Though no wormholes have ever been observed, and most physicists believe they cannot exist in nature due to quantum effects, they represent legitimate solutions to Einstein's equations, demonstrating the incredible flexibility of curved space-time geometry. The mathematical tools needed to work with these curved geometries were largely developed by mathematicians in the 19th century, decades before Einstein needed them for his theory of gravity. Riemann, Christoffel, Ricci, and Levi-Civita created the mathematical machinery of differential geometry without knowing it would someday describe the fundamental structure of space and time. Einstein later remarked that without their mathematical groundwork, he could never have formulated his theory of general relativity. Understanding the shape of space-time requires thinking in 4 dimensions while visualizing effects that extend beyond ordinary human experience. The curvature that determines planetary orbits governs the flow of time and shapes the large-scale structure of the universe, all emerge from the elegant mathematical relationship between geometry and matter encoded in Einstein's field equations. Yet, despite the mathematical complexity, the underlying physical principle remains beautifully simple. Mass and energy tell space-time how to curve, and curved space-time tells matter how to move. Every gravitational phenomenon, from the fall of an apple to the collision of black holes, results from objects following geodesics through the curved four-dimensional landscape of space-time. And in 2015, scientists achieved something that seemed impossible for decades. They detected the ripples in this curved space-time itself, confirming Einstein's prediction that the fabric of space and time could vibrate like a bell struck by the most violent events in the universe. On September 14, 2015, at 9:51 Coordinated Universal Time, humanity heard the universe ring like a bell. After traveling for over 1 billion years across the cosmos, ripples in space-time itself washed over Earth, stretching and compressing the very fabric of reality by less than 1/10,000th the width of a proton. In that moment, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, detected the merger of two black holes over 1 billion light-years away, confirming Einstein's most audacious prediction about the nature of gravity. Einstein had predicted gravitational waves in 1916, just a year after he published his theory of general relativity. If space-time could be curved by mass and energy, he reasoned, then accelerating masses should create ripples in space-time that propagate outward at the speed of light. Much like a stone thrown into a pond creates waves that spread across the water's surface. But Einstein himself doubted whether these waves could ever be detected, believing they would be far too weak to measure with any conceivable technology. The physics of gravitational waves emerges directly from the non-linear nature of Einstein's field equations. Unlike electromagnetic waves, which are disturbances in electric and magnetic fields that propagate through space-time, gravitational waves are disturbances in space-time itself. As a gravitational wave passes through a region of space, it alternately stretches and compresses distances in perpendicular directions, creating a characteristic quadrupole pattern of distortion. Imagine you're floating in space surrounded by a ring of test particles. As a gravitational wave passes through, the ring would be squeezed into an oval in one direction, while being stretched in the perpendicular direction. Then the pattern would reverse, creating an oscillating distortion that propagates at the speed of light. This stretching and compressing affects not just empty space, but all the matter within it, including the atoms in your body and the rulers you might use to measure distances. The sources of detectable gravitational waves must involve some of the most extreme events in the universe. Ordinary accelerating objects, like cars changing speed or even planets orbiting stars, do produce gravitational waves, but these are unimaginably weak. To create waves strong enough to detect across intergalactic distances requires the most violent accelerations of the most massive objects nature can provide. Binary black hole mergers represent the ultimate gravitational wave factories. When two black holes spiral into each other, they create a cosmic whirlpool of distorted space-time. As they orbit closer and closer together, they accelerate to incredible speeds, eventually reaching a significant fraction of the speed of light just before they merge. The final fraction of a second releases more energy in gravitational waves than all the stars in the observable universe emit in light. The signal detected by LIGO on September 14th came from two black holes, one about 36 times the mass of our Sun, and the other about 29 solar masses, that had been locked in their final death spiral for millions of years. In the last few minutes before merger, they completed hundreds of orbits, accelerating to ever higher speeds as gravitational wave radiation carried away their orbital energy. The final collision lasted only about 0.2 of a second, but in that brief time, the system radiated 3 solar masses worth of energy purely in the form of gravitational waves. The detection itself required technology at the very limits of human engineering capability. LIGO consists of 2 L-shaped detectors, one in Hanford, Washington, and another in Livingston, Louisiana, each with arms 4 kilometers long. Laser light travels back and forth along these arms, and gravitational waves passing through Earth stretch one arm while compressing the other, creating tiny changes in the time it takes light to make the round trip. The sensitivity required to detect these changes defies comprehension. LIGO can measure distance changes smaller than 1/10,000th the width of a proton, which is roughly equivalent to measuring the distance from Earth to the nearest star, to an accuracy smaller than the width of a human hair. This extraordinary precision requires isolating the detectors from every conceivable source of vibration, from passing trucks to ocean waves breaking on distant shores. The mirrors that reflect the laser light must be suspended like pendulums to isolate them from ground vibrations, while feedback systems actively cancel out residual motion. The laser light itself must be stabilized to incredible precision, and the entire system must operate in an ultra-high vacuum to prevent air molecules from scattering the light. Even thermal vibrations of the mirror molecules can overwhelm the gravitational wave signal, requiring sophisticated techniques to subtract out this noise. When the first gravitational wave signal swept through the LIGO detectors, it created a distinctive chirp pattern that lasted only 0.2 of a second. The frequency of the waves increased from 35 cycles per second to 250 cycles per second as the black holes spiraled together, then abruptly cut off as the merger completed and the system settled into a single, larger black hole. This chirp pattern exactly matched the predictions of Einstein's theory for a black hole merger, with the specific masses and spins determined by the analysis. The detection represented far more than just confirming Einstein's prediction. It opened an entirely new window on the universe, allowing scientists to observe cosmic events that are completely invisible to traditional telescopes. Black hole mergers produce no light, no radio waves, no X-rays. The only way to study them is through the gravitational waves they generate, as they distort space-time itself. Since that first historic detection, gravitational wave observatories have detected dozens of additional signals. Most have been black hole mergers of various masses and configurations. But on August 17, 2017, LIGO detected something different: the merger of two neutron stars. This event, designated GW170817, was revolutionary because it could be seen both in gravitational waves and in electromagnetic radiation. The neutron-star merger produced a short gamma-ray burst detected by space-based telescopes just 1.7 seconds after the gravitational waves reached Earth. This slight delay confirmed that gravitational waves travel at exactly the speed of light, as Einstein's theory predicted. Over the following days and weeks, telescopes around the world observed the optical infrared and radio afterglow of the merger, creating the first truly multi-messenger astronomical observation. This multi-messenger detection revealed the cosmic factories where many of the heaviest elements in the universe are forged. The neutron-star merger ejected material rich in gold, platinum, and other heavy elements, which we observed as the optical and infrared emission powered by radioactive decay. The total amount of gold created in this single event was estimated to be several times the mass of Earth, providing compelling evidence that neutron star mergers are responsible for much of the gold in your jewelry and electronics. Gravitational wave detections have also provided unprecedented tests of Einstein's theory in the strong field regime, where space-time curvature becomes extreme. The observed waveforms match Einstein's predictions with extraordinary precision, even in the final moments of black hole mergers, where the gravitational fields are billions of times stronger than anything we can create on Earth. The waves also confirmed that gravity propagates at the speed of light, not instantaneously, as Newton's theory suggested. This seemingly simple fact has profound implications for our understanding of causality and the structure of space-time. If gravitational effects could propagate faster than light, it would potentially allow information to be sent backward in time, creating logical paradoxes that would undermine the foundations of physics. Future gravitational wave detectors will be even more sensitive and will cover a broader range of frequencies. The European Virgo detector has joined the global network, allowing scientists to pinpoint the locations of gravitational wave sources much more precisely. The planned LISA mission will place gravitational wave detectors in space using laser interferometry between spacecraft separated by millions of kilometers to detect lower frequency waves from supermassive black hole mergers and other exotic sources. These space-based detectors will open yet another window on the universe, allowing us to observe the mergers of supermassive black holes at the centers of galaxies, the inspiral of stellar mass objects into these galactic giants, and perhaps even the gravitational wave background, left over from the earliest moments after the Big Bang. Each new detection teaches us something fundamental about the nature of gravity, the behavior of matter under extreme conditions, and the evolution of the universe itself. The discovery of gravitational waves represents one of the greatest triumphs in the history of experimental physics. It required developing technology of almost unimaginable precision, international collaboration on an unprecedented scale, and decades of patient work by thousands of scientists and engineers. But perhaps most remarkably, it confirmed predictions made by Einstein over a century ago, using nothing but pen, paper, and the power of human reason. Yet even as gravitational waves have vindicated Einstein's classical theory of gravity, they also point toward the next great frontier in our understanding of the universe, the realm where Einstein's smooth, continuous space-time meets the quantum mechanical world of discrete particles and fundamental uncertainty. Einstein's theory of general relativity is one of the most successful theories in the history of science. It has passed every experimental test, from the bending of starlight to the detection of gravitational waves. It accurately describes the motion of planets, predicts the behavior of black holes, and explains the expansion of the universe itself. Yet despite these triumphs, we know that Einstein's theory is incomplete. There are realms of physics where general relativity breaks down completely, revealing the urgent need for a deeper understanding of gravity that incorporates the strange world of quantum mechanics. The problems begin at the very foundation of how we understand reality. General relativity treats space-time as a smooth, continuous fabric that can be curved and twisted by the presence of mass and energy. But quantum mechanics tells us that at the smallest scales, nothing in the universe is truly smooth or continuous. Energy comes in discrete packets called quanta. Matter exhibits wave-particle duality. Even empty space itself seethes with quantum fluctuations, virtual particles popping into existence and disappearing in timeframes so brief they seem to violate the conservation of energy. This quantum foam, as physicists call it, becomes dominant at incredibly small scales. At distances around the Planck length, about 10 to the minus 35 meters, quantum effects become so strong that our classical notions of space and time cease to make sense. This is 20 orders of magnitude smaller than a proton, a scale so tiny that it defies human comprehension. Yet at this scale, the smooth space-time of Einstein's theory must give way to something fundamentally different, something that incorporates the inherent uncertainty and discreteness of quantum mechanics. The collision between general relativity and quantum mechanics becomes unavoidable when we try to understand black holes. Einstein's theory predicts that matter falling into a black hole eventually reaches a point called the singularity, where density becomes infinite and space-time curvature becomes infinitely strong. At this point, the theory literally breaks down. The mathematical equations produce infinities that have no physical meaning, suggesting that some new physics must take over before the singularity is reached. Stephen Hawking's groundbreaking work in the 1970s revealed another fundamental problem with our understanding of black holes. Using quantum field theory in the curved space-time around a black hole, Hawking showed that black holes should actually emit radiation and and slowly evaporate over time. This Hawking radiation emerges from quantum fluctuations near the event horizon, where virtual particle pairs are separated by the black hole's immense gravity, allowing one particle to escape while the other falls in. The problem with Hawking radiation isn't that it exists, but what it implies about information. When a black hole forms from the collapse of a star, all the detailed information about the star's composition, the quantum states of its atoms, and the specific way it collapsed seems to disappear behind the event horizon. If the black hole then evaporates completely via Hawking radiation, this information appears to be lost forever, violating one of the fundamental principles of quantum mechanics that information must be conserved. This information paradox represents a deep conflict between general relativity and quantum mechanics. Einstein's theory suggests that information falling into a black hole is simply hidden behind the event horizon, neither created nor destroyed. But quantum mechanics insists that information cannot be lost, even in the most extreme circumstances. The resolution of this paradox likely requires a quantum theory of gravity that doesn't yet exist. The problems become even more acute when we try to understand the very beginning of the universe. According to general relativity, if we trace the expansion of the universe backward in time, we reach a moment when all matter and energy was concentrated in a point of infinite density called the Big Bang singularity. Like the singularity at the center of a black hole, this represents a breakdown of Einstein's theory, a moment when the curvature of space-time becomes so extreme that the equations lose all meaning. Quantum mechanics suggests that such singularities cannot actually exist. The uncertainty principle prevents us from knowing both the position and momentum of particles with perfect precision, which should prevent matter from being compressed to a point of zero size and infinite density. But without a quantum theory of gravity, we cannot describe what actually happened at the moment of the Big Bang, or what, if anything, came before it. The incompatibility between general relativity and quantum mechanics also manifests in more subtle ways. In quantum field theory, even empty space is filled with quantum fluctuations that should contribute to the energy density of the vacuum. When physicists try to calculate this vacuum energy density using quantum mechanics, they get an answer that is larger than the observed energy density of the entire universe by a factor of 10 to the 120th power. This is the largest disagreement between theory and observation in the history of science. This vacuum energy should act as a cosmological constant, causing space itself to expand at an ever-accelerating rate. We do observe such acceleration in the expansion of the universe, attributed to something called dark energy, but the magnitude is tiny compared to what quantum mechanics predicts. Either our understanding of quantum vacuum fluctuations is fundamentally wrong, or there's some unknown mechanism that cancels out almost all of this vacuum energy with incredible precision. The quest for a quantum theory of gravity has led physicists down many different paths, each attempting to reconcile the smooth geometry of general relativity with the discrete, probabilistic nature of quantum mechanics. String theory proposes that the fundamental constituents of reality are not point particles, but tiny vibrating strings in multiple dimensions. Loop quantum gravity suggests that space-time itself is made of discrete, quantized units at the Planck scale. Some approaches, like causal dynamical triangulation, attempt to build space-time from fundamental building blocks, much like matter is built from atoms. Others, such as emergent gravity theories, propose that space-time and gravity are not fundamental at all, but emerge from more basic quantum mechanical processes, much like temperature emerges from the motion of molecules. Each of these approaches faces enormous challenges. String theory requires extra dimensions beyond the four we observe, and most versions predict a vast landscape of possible universes with no clear way to determine which one corresponds to our reality. Loop quantum gravity struggles to recover Einstein's theory in the limit where quantum effects become negligible. Emergent gravity theories have difficulty explaining why gravity appears so geometric and why Einstein's theory works so well in the classical limit. The experimental challenges are equally daunting. The energy scales where quantum gravitational effects become important are so extreme that they cannot be reproduced in any conceivable laboratory experiment. The Large Hadron Collider, the most powerful particle accelerator ever built, reaches energies that are still 16 orders of magnitude too small to probe quantum gravity directly. This means that progress in quantum gravity must rely heavily on theoretical insights and indirect observational evidence. Some hope comes from the study of the cosmic microwave background radiation, the afterglow of the Big Bang that fills the entire universe. Tiny fluctuations in this radiation may preserve imprints of quantum gravitational effects from the earliest moments of cosmic history. Similarly, the detection of gravitational waves from the mergers of black holes may eventually reveal signatures of quantum gravity in the final moments before the singularity is reached. Black holes themselves serve as natural laboratories for testing ideas about quantum gravity. The interplay between general relativity and quantum mechanics near the event horizon creates phenomena that have no analogue anywhere else in the universe. As our ability to observe black holes improves, from the first images captured by the Event Horizon Telescope to future gravitational wave detectors with unprecedented sensitivity, we may finally begin to glimpse the quantum nature of gravity. The failure of general relativity at the quantum scale doesn't diminish Einstein's achievement. His theory remains one of the most beautiful and successful descriptions of nature ever devised. But like Newton's theory before it, general relativity appears to be a limiting case of some deeper, more fundamental theory that incorporates both the geometric nature of gravity and the quantum mechanical nature of matter and energy. The search for this quantum theory of gravity represents one of the greatest challenges in modern physics. It requires not just new mathematics and new experiments, but potentially a completely new way of thinking about the nature of space, time, and reality itself. The prize for success would be nothing less than a complete understanding of how gravity works at the most fundamental level, unifying our description of the largest and smallest scales in the universe. Until we achieve this unification, the deepest questions about gravity remain unanswered. What is gravity at the quantum level? Does it consist of particles, just like the other fundamental forces? In the quantum world, forces are not the mysterious actions at a distance that Newton imagined, nor the curved space-time of Einstein's geometric vision. Instead, forces arise from the exchange of particles, quantum messengers that carry interactions between matter across the void. The electromagnetic force emerges from the exchange of photons, massless particles of light that zip between charged objects at the speed of light. The strong nuclear force that binds protons and neutrons together operates through the exchange of gluons, while the weak nuclear force responsible for certain types of radioactive decay involves the exchange of W and Z bosons. If gravity is to fit into this quantum mechanical picture of nature, it too must have its own force-carrying particle. Physicists call this hypothetical particle the graviton, though no one has ever detected a single graviton, or even proven that gravitons actually exist. The graviton remains the most elusive and mysterious of all the proposed fundamental particles, existing more in the realm of theoretical necessity than experimental reality. The properties that gravitons must have, if they exist, are dictated by the characteristics of gravity itself. Since gravity has infinite range, just like electromagnetism, gravitons must be massless, able to travel at the speed of light without ever slowing down or decaying. Since gravity is always attractive, never repulsive, gravitons cannot carry electric charge or any other property that would allow them to push objects apart rather than pull them together. Most crucially, gravitons must have a quantum mechanical property called spin equal to 2. This spin value determines how gravitons interact with matter and with each other, and it's directly related to the fact that gravity affects the geometry of space-time itself. Photons, which carry the electromagnetic force, have spin 1, while the particles that make up matter, like electrons and quarks, have spin 1/2. The graviton's spin 2 nature makes it fundamentally different from all other known particles, reflecting gravity's unique role as the force that shapes space and time. The concept of gravitons emerged from attempts to apply the successful techniques of quantum field theory to gravity. In the 1930s and 40s, physicists developed a powerful framework for understanding electromagnetic interactions in terms of photon exchange. When an electron absorbs or emits a photon, its energy and momentum change in precise ways that can be calculated using the rules of quantum mechanics. This approach, known as quantum electrodynamics, became the most accurate theory in the history of science, with predictions that match experimental observations to more than 10 decimal places. The natural question arose: could gravity be understood in the same way? Could the gravitational attraction between two masses be explained as the result of graviton exchange, just as electromagnetic attraction and repulsion result from photon exchange? In the simplest version of this picture, when two massive objects attract each other gravitationally, they do so by constantly exchanging virtual gravitons, quantum particles that exist for such brief moments that they cannot be directly observed, but whose effects accumulate to create the gravitational force we experience. This graviton exchange picture leads to some fascinating implications. According to quantum field theory, gravitons should interact not only with matter, but also with each other. Unlike photons, which are electrically neutral and don't directly interact with other photons, gravitons carry energy, and since energy gravitates, gravitons should exert gravitational forces on other gravitons. This means that in regions where gravitational fields are very strong, gravitons should interact with themselves, creating nonlinear effects that go beyond simple particle exchange. These graviton self-interactions are precisely what Einstein's general relativity predicts in its nonlinear field equations. The fact that space-time curvature depends not just on matter and energy, but also on the curvature itself, reflects the quantum field theory prediction that gravitons should interact with each other. This remarkable correspondence between Einstein's geometric theory and the particle picture provides compelling evidence that gravitons, if they exist, must behave exactly as quantum field theory predicts. But detecting individual gravitons presents challenges that dwarf even the most difficult experiments in particle physics. The gravitational force is extraordinarily weak compared to the other fundamental forces. It takes the entire mass of Earth to create enough gravitational force to make an apple fall, while a tiny magnet can easily overcome Earth's gravity and pick up a paperclip. This weakness means that individual gravitons carry incredibly small amounts of energy and interact with matter so rarely that detecting them seems practically impossible. To understand just how weak gravitational interactions are, consider that a typical graviton produced by the motion of ordinary matter would have an energy so small that it could pass through a detector made of solid lead stretching from Earth to the nearest star without interacting even once. The probability of a single graviton being absorbed by any conceivable detector is vanishingly small, making direct graviton detection appear hopeless with any technology we can imagine. Yet gravitons, if they exist, should be produced in vast numbers by any accelerating mass. When you wave your hand, quantum field theory predicts that you emit gravitons, though far too few and too weak to detect. More dramatically, the collision of black holes that LIGO observes should produce enormous numbers of gravitons, classical gravitational waves being composed of countless individual gravitons in much the same way that a radio wave is composed of countless photons. The graviton picture also provides new insights into some of the deepest puzzles in physics. The hierarchy problem, which asks why gravity is so much weaker than the other fundamental forces. becomes a question about why gravitons interact so weakly with matter compared to photons, gluons, and W and Z bosons. Some theories propose that gravitons can escape our three-dimensional space and spread out into extra dimensions, diluting their effects and explaining why gravity appears so weak in our everyday experience. String theory, one of the leading candidates for a quantum theory of gravity, naturally incorporates gravitons as one of the fundamental vibrational modes of tiny strings. In this picture, a graviton is simply a string vibrating in a particular pattern, while other particles like photons and electrons correspond to strings vibrating in different ways. String theory predicts that gravitons must exist as a necessary consequence of the mathematical consistency of the theory, providing theoretical support for their reality, even in the absence of direct experimental evidence. Loop quantum gravity, an alternative approach to quantum gravity, takes a different view of gravitons. In this theory, space itself is made of discrete, quantized units, and gravitons emerge as collective excitations of this quantized geometry, somewhat like sound waves emerging from the vibrations of atoms in a solid material. This perspective suggests that gravitons might not be fundamental particles at all, but rather emergent phenomena arising from the deeper quantum structure of space-time. The search for indirect evidence of gravitons continues through increasingly sensitive experiments. While we cannot detect individual gravitons, we can look for quantum effects in gravitational phenomena that would confirm the particle nature of gravity. Some theories predict that gravitons should exhibit quantum entanglement, creating correlations between distant gravitational effects that could be observed in precision measurements of space-time curvature. Future experiments may also probe the quantum nature of gravity through the study of extremely small masses near the quantum limit. As technology advances, physicists hope to create quantum superposition states of objects massive enough to produce measurable gravitational effects, potentially revealing the discrete, quantized nature of gravitational interactions predicted by graviton theory. The cosmic microwave background radiation, the afterglow of the Big Bang, may also preserve signatures of gravitons from the earliest moments of the universe. Theories of cosmic inflation predict that quantum fluctuations of gravitons in the early universe should have left characteristic patterns in this radiation, patterns that future space-based telescopes may be sensitive enough to detect. Even black holes may provide evidence for gravitons. The information paradox that puzzles physicists studying black hole evaporation might be resolved by understanding the quantum mechanical properties of gravitons and how they carry information away from black holes during the Hawking radiation process. Some theories suggest that gravitons could provide a mechanism for preserving information even as black holes evaporate completely. The graviton remains a theoretical construct, a particle that must exist if our quantum mechanical understanding of nature is complete, but which may forever remain beyond direct experimental verification. Its existence would represent the final piece in the puzzle of unifying all fundamental forces under the quantum mechanical framework that has been so successful in describing the electromagnetic, weak, and strong nuclear forces. Whether gravitons are real particles, emergent phenomena, or something else entirely, they represent our best current guess for how gravity might work at the quantum level. They embody the hope that gravity, like all other forces, will eventually yield its secrets to the powerful tools of quantum field theory and reveal its place in the grand unified picture of nature. But what if gravity isn't fundamental at all? What if it's not a force carried by particles, but something much stranger, an illusion that emerges from deeper processes we're only beginning to understand? Temperature doesn't exist. This may sound absurd, but it's true in a fundamental sense. Temperature is not a property that individual atoms possess. An atom cannot be hot or cold by itself. Instead, temperature emerges from the collective motion of vast numbers of atoms. a statistical property that only makes sense when you have many particles moving randomly in different directions. The faster the average motion, the higher the temperature. But look at any single atom, and the concept of temperature becomes meaningless. This realization has led some physicists to wonder, could gravity be similar to temperature? Could it be an emergent phenomenon that arises from deeper, more fundamental processes rather than a basic force of nature? This radical idea challenges everything we think we know about gravity, suggesting that Einstein's curved spacetime and Newton's universal attraction might both be illusions, statistical effects that emerge when you have enormous numbers of quantum mechanical processes happening simultaneously. The concept of emergent gravity gained serious scientific attention in the early 21st century, driven by insights from thermodynamics, information theory, and string theory. The fundamental observation is that gravity appears to be intimately connected with entropy, the measure of disorder or information content in a system. This connection was first noticed in the study of black holes, where Jacob Bekenstein and Stephen Hawking discovered that black holes have temperature and entropy, despite being among the simplest objects in the universe. The entropy of a black hole turns out to be proportional to the area of its event horizon, not its volume, as you might expect. This was puzzling because we normally think of entropy as being related to the number of particles or the amount of stuff inside a region of space. But black hole entropy depends only on the surface area of the horizon, suggesting that all the information about the black hole's interior is somehow encoded on its two-dimensional boundary. This observation led to the holographic principle, one of the most revolutionary ideas in modern physics. The holographic principle suggests that all the information in any three-dimensional region of space can be encoded on its two-dimensional boundary, much like a hologram encodes a three-dimensional image on a flat surface. If this principle is correct, then our three-dimensional universe might be a kind of hologram, a projection of information that actually lives on some distant two-dimensional surface. Juan Maldacena's discovery of the ADS-CFT correspondence in 1997 provided the first concrete example of holographic duality. He showed that certain theories of gravity in curved spacetime are mathematically equivalent to quantum field theories, without gravity living on the boundary of that spacetime. In this correspondence, gravitational phenomena in the bulk space emerge from quantum entanglement and information processing on the boundary, suggesting that gravity might not be fundamental, but rather a holographic projection of more basic quantum mechanical processes. Building on these insights, Eric Verlinde proposed in 2010 that gravity could be understood as an entropic force, similar to the force that pulls together the two ends of a stretched polymer molecule. In Verlinde's picture, space-time itself is made of more fundamental units of information, and what we perceive as gravitational attraction is actually the tendency of these information units to maximize their entropy, just as the random motion of molecules creates pressure and temperature in a gas. According to entropic gravity theory, when matter is present in space-time, it reduces the number of ways that information can be arranged, decreasing the total entropy of the system. The apparent gravitational force that attracts matter together is actually the information trying to restore maximum entropy by spreading out more evenly. In this view, Newton's law of gravity and Einstein's curved spacetime are both statistical approximations that emerge when you average over enormous numbers of microscopic information processing events. Verlinde's theory makes specific predictions that can be tested against observations. It correctly reproduces Newton's laws of gravity and many aspects of Einstein's general relativity in the appropriate limits. More remarkably, it predicts the existence of an additional entropic force that depends on the total amount of matter in the universe, potentially explaining the mysterious dark matter that seems to dominate the gravity of galaxies and galaxy clusters. Traditional dark matter theories propose that galaxies are embedded in massive halos of invisible particles that interact gravitationally but not electromagnetically. These dark matter particles have never been directly detected despite decades of searching with increasingly sensitive experiments. Verlinder's entropic gravity offers an alternative explanation. The apparent effects of dark matter might actually be additional entropic forces that arise when you properly account for the information content of the cosmic horizon. The idea that gravity emerges from information processing gains support from other areas of theoretical physics. The holographic principle suggests that the event horizon of a black hole functions like a computer, processing information at the fundamental limit set by quantum mechanics. The Bekenstein bound shows that any region of space can contain only a finite amount of information, determined by its surface area rather than its volume. These information-theoretic limits appear to be closely related to gravitational phenomena. The acceleration of expanding spacetime seems to be connected to the rate at which information can be processed on the cosmic horizon. The strength of gravitational fields correlates with the information density in spacetime. Even the speed of light might emerge from the fundamental rate at which information can propagate through the quantum mechanical substrate that underlies spacetime. Ted Jacobson showed in 1995 that Einstein's field equations can be derived from the assumption that entropy increases when matter crosses a local horizon, combined with the proportionality between entropy and area discovered in black hole thermodynamics. This suggests that general relativity itself might be a thermodynamic law rather than a fundamental theory of spacetime geometry. The ER equals EPR conjecture, proposed by Leonard Susskind and Juan Maldacena, provides another perspective on emergent gravity. They suggested that quantum entanglement between particles creates wormhole-like connections in spacetime, with Einstein-Rosen bridges being equivalent to Einstein-Podolsky-Rosen entanglement. In this picture, the connectivity of spacetime itself emerges from the pattern of quantum entanglement between matter and energy. If space-time connectivity emerges from entanglement, then gravity might arise from the collective behavior of these quantum correlations. When entanglement patterns change, the geometry of space-time changes, creating what we perceive as gravitational effects. The force that holds the Earth in orbit around the Sun might actually be the manifestation of quantum information flowing through entanglement networks that span the solar system. These ideas suggest that spacetime might be made of discrete units of information, sometimes called "its from bits," after John Wheeler's famous phrase. Each bit of information occupies one unit of area at the Planck scale, and the smooth spacetime of Einstein's theory emerges as a statistical average over enormous numbers of these information units, just as the smooth surface of a liquid emerges from the chaotic motion of individual molecules. Loop quantum gravity provides a concrete realization of this discrete spacetime picture. In this theory, space is composed of finite loops and nodes that carry discrete units of area and volume. The smooth geometry of general relativity emerges when you average over many of these discrete units, similar to how the smooth flow of a river emerges from the motion of individual water molecules. Some approaches to emergent gravity go even further, suggesting that not just gravity, but all of physics might emerge from information processing. In these theories, particles, forces, and even time itself are emergent properties of some underlying computational process. The universe becomes a kind of cosmic computer, with physical laws being the software that runs on the hardware of quantum information. The implications of emergent gravity extend far beyond theoretical physics. If gravity is not fundamental, then our understanding of cosmology, black holes, and the nature of spacetime itself needs to be completely reconsidered. The Big Bang might not be the beginning of spacetime, but rather a phase transition in some more fundamental information processing system. Black holes might not be objects in spacetime, but rather glitches in the computational process that underlies reality. Experimental tests of emergent gravity theories are challenging because the predicted deviations from Einstein's theory are typically very small, except in extreme conditions. However, precision measurements of gravitational effects in galaxy clusters, studies of the cosmic microwave background radiation, and observations of black hole mergers may eventually reveal signatures of the underlying discrete or emergent nature of space-time. The possibility that gravity is emergent, rather than fundamental, represents one of the most radical ideas in modern physics. It suggests that our most basic intuitions about space, time, and causation might be wrong, that what we perceive as the arena in which physics takes place is actually itself a product of more fundamental physical processes. Whether gravity emerges from thermodynamics, quantum entanglement, information theory, or some combination of these ideas remains an open question. But the mere possibility that gravity might not be fundamental challenges us to think more deeply about the nature of reality itself and the role that information and computation might play in the structure of the universe. Even if gravity is emergent, it continues to shape the largest structures in the cosmos, determining the fate of stars, galaxies, and the universe itself through its cosmic competition with the mysterious force driving cosmic acceleration. Gravity is the architect of the cosmos. Over billions of years, it has sculpted the universe from a nearly smooth sea of hydrogen and helium into the magnificent hierarchy of structures we observe today. Stars igniting in stellar nurseries, galaxies spinning through space in elegant spirals, and vast cosmic webs stretching across hundreds of millions of light years. Every star that shines, every planet that harbors life, every black hole that warps space-time owes its existence to gravity's patient, inexorable pull. In the beginning, just a few 100,000 years after the Big Bang, the universe was remarkably uniform. The cosmic microwave background radiation shows us a snapshot of this early epoch, revealing temperature variations of only a few parts in 100,000 across the entire observable universe. But even these tiny fluctuations were enough for gravity to begin its cosmic construction project, slowly gathering matter into the seeds that would eventually become galaxies and stars. The process began with dark matter, the mysterious substance that outweighs ordinary matter by a factor of 5 to 1. Dark matter feels only the gravitational force, ignoring the electromagnetic interactions that heat and pressure ordinary matter. This made dark matter the first to respond to gravity's call, clumping together into vast halos that served as gravitational scaffolding for the ordinary matter that would eventually form stars and planets. As ordinary matter fell into these dark matter halos, it experienced a different fate. Unlike dark matter, ordinary matter could radiate away energy through electromagnetic processes, allowing it to cool and condense more efficiently. Gas clouds contracted under their own gravity until they reached the critical densities and temperatures needed to ignite nuclear fusion, transforming gravitational potential energy into the light and heat of the first stars. These primordial stars were massive giants, burning bright and dying young in spectacular supernova explosions that scattered heavy elements throughout space. Each generation of stars lived and died under gravity's influence, building up the periodic table one fusion reaction at a time, creating the carbon, oxygen, silicon, and iron that would eventually become rocky planets and living beings. Gravity governs not just the birth of stars, but their deaths as well. When a star exhausts its nuclear fuel, gravity finally wins its long battle against the outward pressure of fusion. For stars like our Sun, gravity compresses the stellar core into a white dwarf, an Earth-sized ember that slowly cools over trillions of years. More massive stars meet more dramatic fates, their cores collapsing so violently that they trigger supernova explosions visible across billions of light years. The most massive stars of all experience the ultimate triumph of gravity. When their cores collapse, not even the quantum mechanical pressure of neutrons can resist gravity's pull. The core contracts past the neutron star phase, past any known form of matter, creating a region where space-time curvature becomes so extreme that not even light can escape. A black hole is born, a testament to gravity's ability to curve space-time so severely that it creates a one-way boundary in the fabric of reality itself. Black holes continue to grow throughout their lives, accreting matter from their surroundings and merging with other black holes in violent collisions that send gravitational waves rippling across the universe. At the centers of galaxies, supermassive black holes, millions or billions of times more massive than the Sun, regulate star formation across their entire galactic neighborhoods, their gravitational influence extending far beyond their event horizons. The competition between gravity and gas pressure creates a delicate balance that determines which regions of a galaxy can form new stars. Too little gravity, and gas remains diffuse and unable to collapse. Too much gravity, particularly from a central supermassive black hole, and gas becomes too hot and turbulent to condense into stars. This cosmic thermostat, regulated by gravity's interaction with electromagnetic forces, controls the rate at which galaxies convert their gas into stars. On larger scales, gravity continues to drive cosmic evolution by pulling galaxies together into clusters and superclusters. The Milky Way is part of the Local Group, a small collection of galaxies dominated by our galaxy and the nearby Andromeda Galaxy. In about 4.5 billion years, gravity will pull these two giant spirals together in a slow-motion collision that will reshape both galaxies and eventually merge them into a single larger elliptical galaxy. Galaxy clusters, the largest gravitationally bound structures in the universe, contain hundreds or thousands of individual galaxies held together by gravity. These clusters are so massive that they bend space-time enough to act as gravitational lenses, magnifying and distorting the images of even more distant galaxies behind them. The hot gas between galaxies in these clusters glows with X-ray emission, heated to millions of degrees by the gravitational energy released as matter falls into the cluster's gravitational well. But gravity faces a cosmic adversary in its quest to pull the universe together. Dark energy, a mysterious force that causes space itself to expand at an accelerating rate, opposes gravity on the largest scales. While gravity tries to pull matter together, dark energy drives galaxies apart, stretching the fabric of space-time and carrying distant galaxies away from us at ever-increasing speeds. This cosmic tug-of-war between gravity and dark energy determines the ultimate fate of the universe. Current observations suggest that dark energy is winning, causing the expansion of space to accelerate rather than slow down. If this continues, the universe will enter a phase called the Big Rip, where dark energy becomes so dominant that it overcomes gravity even on small scales, eventually tearing apart galaxies, stars, planets, and even atoms themselves. Alternatively, if dark energy weakens over time, or if there's more dark matter than we currently estimate, gravity might eventually halt the cosmic expansion and reverse it, causing the universe to collapse back on itself in a big crunch. In this scenario, all the structure that gravity has built over billions of years would be destroyed as galaxies, stars, and planets fall together into an increasingly hot and dense cosmic fireball. The most likely scenario, based on current observations, is neither a big rip nor a big crunch, but rather a gradual heat death of the universe. In this future, dark energy continues to drive cosmic expansion, while gravity slowly wins local battles, pulling matter together into increasingly massive black holes. Star formation will gradually cease as galaxies exhaust their gas supplies, and the universe will grow darker and colder as existing stars burn out and die. Even in this far future dominated by black holes, gravity will continue to shape cosmic evolution. Black holes will slowly evaporate through Hawking radiation, with smaller black holes disappearing first and supermassive black holes taking an almost unimaginably long time to completely evaporate. A black hole with the mass of our Sun would take 10 to the 67th years to evaporate completely, a time span so vast that it makes the current age of the universe seem like an instant. During this incredibly long phase of cosmic evolution, gravity will drive the slow decay of all remaining matter. Protons themselves may be unstable over these vast timescales, eventually decaying into lighter particles and energy. If so, even the atoms that make up planets and stars will eventually disintegrate, leaving behind only electrons, positrons, neutrinos, and photons in an ever-expanding, ever-cooling universe. In the ultimate far future, perhaps 10 to the 100 years from now, even black holes will have evaporated completely, leaving behind only a thin gas of elementary particles in a universe that has expanded to unimaginable size. The temperature will approach absolute zero, and the density of matter will become so low that particles may never encounter each other again. This is the heat death scenario, where entropy reaches its maximum value and no further organized activity is possible. Yet even in this seemingly final state, gravity may have one last surprise. Some theories suggest that quantum tunneling could allow the vacuum of space to spontaneously decay to a lower energy state, creating bubble universes that expand at the speed of light and reset the cosmic clock. Other theories propose that the evaporation of black holes could create baby universes, new cosmic regions that branch off from our own and begin their own cycles of expansion and evolution. The role of gravity in determining cosmic fate extends beyond just the mechanics of cosmic expansion and contraction. Gravity created the conditions necessary for life by forming stable planetary systems around long-lived stars. It drives the plate tectonics that recycle Earth's surface and maintain our planet's magnetic field. It creates the tidal forces that may have helped jumpstart the chemical processes that led to the origin of life. Even the elements essential for life owe their existence to gravity. Carbon, oxygen, nitrogen, and phosphorus were all forged in the cores of massive stars under the extreme pressures created by gravitational collapse. When these stars exploded as supernovae, gravity's role in stellar evolution scattered these life-giving elements throughout space, seeding future generations of stars and planets with the raw materials needed for complexity and consciousness. Looking ahead, gravity will continue to play a crucial role in humanity's future as we become a spacefaring species. Understanding gravitational effects is essential for navigation in space, for landing on other worlds, and for detecting potentially habitable planets around distant stars. The gravitational waves that LIGO detects provide a new way to study the universe and may eventually enable us to probe cosmic events that are invisible to traditional telescopes. Gravity has been the dominant force shaping cosmic evolution for nearly 14 billion years, and it will continue to influence the fate of the universe for countless eons to come. Whether the universe ends in fire or ice, whether consciousness spreads throughout the cosmos or remains confined to Earth, gravity will play a central role in determining how the cosmic story unfolds. But what is gravity, really? After journeying through its effects from falling apples to colliding black holes, from Newton's laws to Einstein's geometry, from quantum particles to emergent information, we return to the fundamental question that has driven this entire exploration. We began this journey with a simple question: how does gravity actually work? We've traveled from Newton's falling apple to Einstein's curved spacetime, from the detection of gravitational waves to the search for quantum gravity, from the possibility of gravitons to theories of emergent spacetime. Now, as we reach the end of our exploration, we find ourselves confronting a beautiful paradox. The more we understand about gravity, the more mysterious it becomes. Gravity defies easy categorization. It's simultaneously the most familiar and the most alien of nature's forces. Every human being has experienced gravity from their first breath to their last, yet it operates according to principles that challenge our deepest intuitions about space, time, and reality itself. It's the weakest of the fundamental forces, so feeble that a small magnet can overcome the gravitational pull of the entire Earth. Yet it dominates the large-scale structure of the universe and determines the fate of stars, galaxies, and cosmos itself. Newton gave us our first scientific understanding of gravity as a universal force of attraction between masses. His inverse square law revealed the mathematical harmony underlying planetary motion and terrestrial physics, showing that the same force that pulls an apple toward Earth also keeps the moon in its orbit. For more than 2 centuries, Newton's theory provided an accurate description of gravitational phenomena, enabling precise predictions of planetary positions, the discovery of new worlds, and the engineering marvels of the industrial age. But Newton's gravity came with a philosophical price: action at a distance. How could the Sun instantly know about Earth's presence across 93 million miles of empty space? Newton himself was troubled by this question, famously declaring that he would frame no hypotheses about the mechanism behind gravitational attraction. He had described what gravity did with extraordinary precision, but the question of how it worked remained unanswered. Einstein's revolution changed everything by revealing that gravity isn't a force at all. In his geometric theory of general relativity, massive objects curve the fabric of space-time itself, and other objects simply follow the straightest possible paths through this curved geometry. What we experience as gravitational force is actually our resistance to following these natural geodesic paths through curved space-time. The apple falls not because Earth pulls it down, but because it follows its natural trajectory through the curved space-time around our planet. This geometric understanding of gravity eliminated Newton's troubling action at a distance by showing that gravitational effects propagate through space-time at the speed of light, carried by ripples in the fabric of space and time itself. Einstein's theory made specific, testable predictions that distinguished it from Newton's force-based model, from the bending of starlight to the precise precession of Mercury's orbit. Every experimental test has confirmed Einstein's geometric vision with extraordinary accuracy. The detection of gravitational waves by LIGO provided the most dramatic confirmation yet of Einstein's theory, revealing that space-time itself can vibrate like a cosmic bell when disturbed by the most violent events in the universe. These ripples in reality, predicted by Einstein over a century ago, opened an entirely new window on the cosmos and confirmed that gravity really is the curvature of space-time, not a force reaching across empty space. Yet even Einstein's magnificent theory has its limitations. General relativity breaks down at the quantum scale, where the smooth geometry of curved space-time must somehow give way to the discrete, probabilistic world of quantum mechanics. At the centers of black holes and at the moment of the Big Bang, Einstein's equations predict infinite curvatures that signal the breakdown of the theory itself, pointing toward the need for a quantum theory of gravity that doesn't yet exist. The search for this quantum theory has led physicists to consider radical possibilities. Perhaps gravity consists of massless, spin-2 particles called gravitons that mediate gravitational interactions just as photons mediate electromagnetic forces. These hypothetical gravitons would be produced in vast numbers by accelerating masses and would interact with each other in ways that reproduce the non-linear effects of Einstein's curved space-time. But gravitons remain purely theoretical, far too weakly interacting to detect directly with any conceivable technology. Alternatively, gravity might not be fundamental at all, but rather an emergent phenomenon that arises from deeper quantum mechanical processes, much like temperature emerges from the motion of atoms, or pressure emerges from molecular collisions. In these theories, space-time itself might be made of discrete units of information, and what we perceive as gravitational attraction could be the statistical result of information processing at the Planck scale, below the threshold of direct observation. The holographic principle suggests that all the information in any three-dimensional region of space might be encoded on its two-dimensional boundary, making our familiar three-dimensional world a kind of projection from a more fundamental two-dimensional reality. If this principle is correct, then gravity in our three-dimensional space emerges from quantum entanglement and information processing on some distant boundary, challenging our most basic assumptions about the nature of space, time, and causality. These competing pictures of gravity, geometric, particle-based, emergent, and holographic, each capture different aspects of gravitational phenomena, while leaving other questions unanswered. Einstein's curved spacetime provides an elegant description of gravity in the classical limit, but struggles to incorporate quantum effects. Graviton theories promise to unify gravity with the other fundamental forces, but predict effects too weak to observe directly. Emergent gravity theories offer new perspectives on dark matter and cosmology, but remain highly speculative and difficult to test. Perhaps the ultimate answer is that gravity is all of these things simultaneously, different facets of a more fundamental reality that we glimpse only partially through our current theories. Einstein's curved spacetime might be the large-scale, statistical average of quantum gravitational processes involving gravitons or discrete spacetime units. The geometric and particle pictures might be complementary descriptions of the same underlying physics, much like wave and particle descriptions of light capture different aspects of electromagnetic phenomena. The profound mystery of gravity extends beyond its mechanism to its very existence. Why does gravity exist at all? Why is it so much weaker than the other fundamental forces? Why does it have exactly the properties it does, with an inverse square law that allows stable planetary orbits and a universal coupling that affects all forms of matter and energy equally? These questions touch on some of the deepest issues in physics and cosmology, potentially requiring us to understand not just how gravity works, but why the universe is structured in a way that allows gravity to exist. The anthropic principle suggests that gravity's properties might be finely tuned to allow the existence of stars, planets, and life itself. If gravity were slightly stronger, stars would burn out too quickly for life to evolve. If it were slightly weaker, stars might never form at all, leaving the universe a cold, dark expanse of hydrogen and helium. The precise value of gravity's strength appears to be one of many cosmic coincidences that make our existence possible, though whether this represents genuine fine-tuning or simply selection bias remains hotly debated. Looking toward the future, our understanding of gravity will continue to evolve as new experiments probe ever more extreme regimes and more sensitive instruments detect ever subtler effects. The Event Horizon Telescope has begun to image the shadows of black holes, revealing the structure of spacetime in the strongest gravitational fields in the universe. Future gravitational wave detectors will observe cosmic events with unprecedented sensitivity, potentially revealing signatures of quantum gravity or extra dimensions. Space-based experiments may eventually test the equivalence principle with exquisite precision, searching for tiny violations that could point toward new physics beyond Einstein's theory. Precision measurements of the cosmic microwave background might reveal imprints of quantum gravitational effects from the earliest moments of cosmic history. And if we're very fortunate, the Large Hadron Collider or its successors might create microscopic black holes or extra-dimensional effects that could illuminate the quantum nature of gravity. But even if we someday achieve a complete quantum theory of gravity, even if we understand exactly how gravitons work, or how space-time emerges from more fundamental processes, gravity will retain its special status in physics. It's the force that shapes the universe on the largest scales, that creates the conditions necessary for complexity and consciousness, that will ultimately determine the fate of everything that exists. Gravity is geometry. Gravity is information. Gravity is the curvature of space-time and the exchange of virtual particles and the emergent statistics of quantum processes all rolled into one. It's the force that isn't a force, the field that is space-time itself, the phenomenon that bridges the classical and quantum worlds while belonging fully to neither. In the end, perhaps the most honest answer to our original question is that gravity works by being gravity, by having the unique properties that make it simultaneously the most universal and the most mysterious aspect of physical reality. It works by curving space-time, by exchanging gravitons, by processing information, by emerging from quantum entanglement, by all of these mechanisms, and possibly by others we haven't yet imagined. What we can say with certainty is that gravity, whatever its ultimate nature, is fundamental to everything we observe and experience. Without it, there would be no stars to light the cosmos, no planets to harbor life, no galaxies to organize matter into magnificent structures spanning billions of light years. Gravity is the invisible architect of reality, the silent curator of cosmic evolution, the force that binds the universe together while simultaneously driving its expansion toward an uncertain future. We call it gravity, but it's not a pull, it's the shape of space itself. It doesn't act, it is. A silent curvature, a whisper in space-time, the echo of mass and motion across the cosmos, and we are its travelers. In the quiet moments before dawn, when the world lies still and the stars fade into morning light, gravity continues its eternal work. It holds the Earth steady in its orbit, keeps the atmosphere wrapped around our planet like a protective blanket, and ensures that every drop of morning dew will fall gently to the ground. In these peaceful moments, it's easy to forget that we're witnessing one of the universe's greatest mysteries in action. Our journey through the nature of gravity has taken us from the familiar sensation of weight to the exotic physics of black hole mergers, from Newton's mathematical insights to Einstein's geometric revolution, from the hunt for gravitons to theories that space-time itself might emerge from quantum information. At every step, we've discovered that gravity refuses to be captured by simple explanations or reduced to familiar analogies. It remains beautifully, stubbornly mysterious. We've learned that gravity is simultaneously the weakest and strongest force in nature. Weak enough that a child's balloon filled with helium can overcome the gravitational pull of the entire Earth, yet strong enough to bind galaxies together across millions of light years and to curve the very fabric of space-time around massive objects. This paradox runs through every aspect of gravitational physics, reminding us that the universe operates on scales and according to principles that stretch far beyond our everyday experience. The story of our understanding of gravity is also the story of human curiosity and ingenuity. From ancient astronomers tracking the motions of planets, to modern physicists detecting gravitational waves from colliding black holes billions of light years away, each generation has pushed the boundaries of what seemed possible to observe and understand. The technologies we've developed to study gravity, from Galileo's telescope to LIGO's laser interferometers, represent some of humanity's greatest achievements in precision measurement and engineering. Yet for all our progress, fundamental questions remain. We still don't know whether gravity consists of particles called gravitons or emerges from deeper quantum processes. We don't understand why gravity is so much weaker than the other forces. or why it has exactly the properties needed to create a universe capable of supporting complex structures and life. We don't know whether space-time is truly continuous, as Einstein envisioned, or made of discrete units, as quantum theories suggest. These remaining mysteries aren't failures of our scientific understanding, but rather invitations to continued exploration. Each unanswered question points toward new experiments to design, new theories to develop, and new phenomena to discover. The history of physics teaches us that today's puzzles often become tomorrow's technologies, and today's impossible measurements become routine observations for future generations. The practical implications of our growing understanding of gravity extend far beyond academic curiosity. GPS satellites must account for the effects of gravitational time dilation to maintain their accuracy. Engineers designing spacecraft must precisely calculate gravitational assists from planets to send probes to the outer solar system. Astronomers use gravitational lensing to study the most distant galaxies and search for planets around other stars. As we look toward the future, gravity will continue to shape both our scientific understanding and our technological capabilities. The next generation of gravitational wave detectors will reveal new types of cosmic events and test Einstein's theory in ever more extreme regimes. Space-based experiments will probe the equivalence principle with unprecedented precision. And perhaps someday, a complete theory of quantum gravity will finally unite our understanding of the very large and very small. But even if we achieve such a unified theory, even if we completely understand how gravity works at every scale from the quantum to the cosmic, gravity will retain its unique status in physics and in human experience. It's the force that shaped the cosmos from its earliest moments, creating the conditions that allowed stars to shine, planets to form, and life to emerge. It's the phenomenon that connects us most directly to the universe at large, reminding us with every step we take that we're part of something vast and magnificent. Gravity teaches us profound lessons about the nature of reality. It shows us that space and time are not the fixed stage on which physics plays out, but are themselves dynamic participants in cosmic evolution. It reveals that the universe is far stranger and more beautiful than our intuitions suggest, operating according to principles that challenge our everyday understanding while remaining perfectly consistent and mathematically elegant. Perhaps most importantly, gravity reminds us of our place in the cosmic order. We are not separate from the universe, but are expressions of it, collections of atoms forged in stellar cores and assembled by gravitational processes that stretch back billions of years. The calcium in our bones was created in dying stars. The iron in our blood was forged in supernova explosions, and the very elements that make up our DNA were scattered through space by gravitational processes and gathered together again to form new worlds and new possibilities for complexity and consciousness. The story of gravity is ultimately the story of connection. It connects every particle to every other particle across the vast expanse of space. It connects the motion of planets to the fall of raindrops. It connects the quantum world of particle physics to the cosmic world of galaxies and black holes. And it connects us to the deepest mysteries of existence, challenging us to understand our universe and our place within it. We call it gravity, but it's not a pull. It's the shape of space itself. It doesn't act, it is. A silent curvature, a whisper in space-time, the echo of mass and motion across the cosmos. And we are its travelers, riding the geodesics of curved space-time through a universe that continues to surprise and inspire us with its hidden depths and magnificent complexity. In the end, gravity remains what it has always been, the invisible thread that weaves together the fabric of reality, the fundamental force that shapes everything from the smallest quantum fluctuations to the largest cosmic structures. It is the shadow of space-time itself, cast by the presence of matter and energy, curved by the dance of mass and motion, and experienced by every conscious being as the gentle but inexorable reminder that we are part of something infinitely larger than ourselves. How does gravity actually work? The answer is that it works by being the universe itself, the stage and the actors, the music and the dance, the question and the answer all rolled into one. It works by being gravity, beautiful, mysterious, and eternal.